Today we are going to discuss about. So hello everyone. Today we are going to discuss about applications of correlation games. So these are the topics which we are going to go through. So first I will give a small introduction about correlation games. So like why it is different from game theory. So correlation game is defined studies the cooperation and coordination between players to maximize their total benefit. So here the players won't compete with each other. They coordinate and form into groups which are known as coalitions. And we are going to speak in mainly three main domains, which is economics, AI and multi-system agents, and network designs. So here the main question is how the profits are divided between the players. So that's the main part. So this is the mathematical formulation of the correlation game. That is how it is represented. So the correlation game is defined as pair of comma B, where M is known as set of players, and here B is known as value function or characteristic function. So this function keeps on changing according to the payoffs of each player. So this is the main part. And there two key properties. First is the superadditive property, and second is the non-transitive property. So here, superadditive property, like if we take any two groups, the combined output, like the combined payoff, should be equal to the union of the two groups. So that is followed. So that is constantly followed by every group. And non-transitive property means like adding more members to a correlation never reduces the value. Like if we add more and more members, pairwise distributions are two or more pairs, so the payoff doesn't decrease. Like it will be constant only. Okay. Next is the Shapley value concept. So like here to solve the problem, like how the payoff is divided equally. So to solve that problem, the Shapley value concept is described. So the Shapley value tells gives a fair payoff distribution among the team players. So it is based on marginal contributions, like each contribution of each player is based on that. So it is represented as contribution of each player, and the estimate is the set of values, and if we add each player into the set, so the contribution margin keeps on increasing, and this is the main formula of the Shapley value, which we use to give a fair distribution, fair contribution among the team players. So here there are four key angles. The first one is the efficiency angle, where like the total payoffs are equally distributed among the members, and which is equals to the combined correlation group payoff. Like correlation of one plus which take two correlation groups, like two groups. Correlation of the correlation group is combination of correlation of correlation. So this is the main concept of efficiency. And second is the symmetry. Symmetry means every player contributes equally. And next, dummy player means like there is zero contribution from the player, like there is zero payoff. And next, additive property means like the super additive property which we have discussed before. This is the Shapley concept. So next is the supply. Let's go to the first application, which is supply chain collaboration. So in most of the companies or enterprises, they use supply chain model for their manufacturing units and different like moving their goods from one place to another place. So here the main concept of correlation game theory is applicable here. So here to make it to take like a small distribution, we are taking three players: the manufacturer, the distributor, and the retailer. So here the goal of each player is to maximize their savings and minimize the costs. So according to the question, let's take it here like individual savings they are given. So individual savings is the value function. The value function of each player. So here the value function of manufacturer is 100. The value function of distributor is 80. The value function of the retailer. So here, like first we will take all combinations. So here there are three here. So there are three factorial combinations. So totally there are 6 combinations. So like you can arrange them here. So let's take the contribution of each pair. So here there is also one more thing to do. It is the total correlation, like the total group contribution. That's the 3. So the total correlation is 300. So let's take one. Let's take this case. The first is MDR. So first, M enters. So why M enters? Like there is no other player in the correlation. So the value of the X contribution would be V of M, which is 100. So this will be 100 for X contribution. So next, as D enters. So then there will be 2 players in the correlation. That is pairwise distribution. Okay. So this would be the total contribution when D enters. So we will remove the M's contribution from it. We will get the D's contribution from the correlation. So this would be so we'll get 100. And next when R enters, then it would be like the correlation would be M D R. So we should remove the MD as well as the D's contribution. So then we will get. So similarly, if we calculate like all contributions, like I will write down and total contributions of each permutation, like each set. Like if you take MDR, then each contribution will be 100, each contribution will be 100. Between MDR and MRD. Here the in the second case, in the first case, like second D enters, but in the MRD concept, like R enters in the second case. Like So that's why the value is like if we calculate. So now the main concept of safety value is to take the average of all contribution margins. So for this, if you take all the average, 100 plus 120 plus 140, 140 by 6. So should be around. Similarly, if we calculate we have a number. So this is the actual contributions of each player. Like for manufacturer is 200. For each player, this is the actual contribution. Like this is the payoff they should get. So that's why we are taking the safety value. So this is the first application. Also, there is one more concept here. Like if we add all the three shaky values, you will get the total what is the total correlation value function, that is 300. You add all this. So this means that there is no extra payoff which is achieved during the process, and efficiency, whatever the efficiency property is, that is satisfied for it. So next. So this is the next application is wireless network cooperation. This is the second application. So in the wireless network cooperation, there are to explain it simply, there are two separate networks, that is BS1 and BS2, and their value functions are given like 50 and 45, and their total correlation network value function is 120 Mbps. So they also share the same bandwidth. So let's take a bandwidth. So here there is a concept called as synergy. Like this is a small entity. This term is used to identify the extra gain or extra payoff is be beneficial for each player during if we divide into different pairwise distributions. So let's calculate the synergy. Like we subtract from the whole correlation. So this is the synergy. Like this is the extra payoff which each player should get. And next, next after this, we will calculate the safety value, because safety value is the main contribution of each player. So let's calculate the safety value of player. Like the network. So according to the formula, this is 100. Next, P of 5 means the empty set case. So we will consider this as 0. And P of 1 means the value comes from 2. And 120. This is the first shaking also. The second one. So the next application is the energy sharing in smart grids. So like here there is a concept called prosumers. Like prosumer means like they will produce and also consume the energy part. This is used in correlation gaming theory to aggregate the generation and demand, optimizing distribution and overall costs. So here also the same agenda as the supply chain model. So here also they will minimize the costs and maximize their profits. So here let's go to the example. Here there are three prosumers, like three players. So here actually whatever we calculate here the synergy, we would add in the pairwise distributions. Here it is 25. So we will take 12.5, 12.5. We will add them in the whole distribution. So that's the main point. So here also if we calculate, we would get the efficiency property will be satisfied, and also here one more thing is they would be we would achieve equal distributions. Equal distributions would achieve, then symmetry property is also satisfied here. So that's one thing. And also each prosumer tries to reduce the cost. So yeah, from here we need to.
So from here I am going to explain this and machine learning and AI application in coalition game. So different components of AI like features and data sets and agents are considered here as a players using game theory, coalition game theory. We can mathematically we can calculate how much each component is giving performance to model, performance of model. Feature importance uses shapely values to identify how much each feature contributes to a specific prediction. Here sharp means shapely additive shapely additive explanations. So that means it gives how each component is performing. So let's consider a case where loan approval system is based on whether income and credit score. If you consider with and without income, it will separate the features and it will isolate its impact. Application card, political alliance. Here political alliance means more than if there are three parties, A have some there are total 100 seats are there, and we have some credit 100 seats are there, then A have some 45 seats, B have some 40 seats, and C has some 15 seats. And even though party C has fewer seats, it becomes essential because it is the deciding factor. Where it can be considered as a kingmaker for the parties, both party A and B. Here, using the shapely value, we can calculate how much power each party does have. So there is a case study on quantifying power in coalition governments. Advantages like models show how working together provides greater benefit. Acting alone, like if you cooperate with Anga and work together, then we can optimize the work and we can get better rewards compared to working alone. Fair distribution, using Shapley value, we can distribute we can distribute the rewards according to their contribution. Optimal resource allocation, like using this Shapley value, we can minimize the waste and maximize the collective value. Predictive power. Analysts can calculate which group structure are most likely to form and stable over time, and this can be used in like AI agents and political parties and public works. Limitation, computational complexity. suppose there are two players, then there may be there are four coalitions. If there are three players, then there are eight coalitions. If there are 10 players, then there may be there are 1024 coalitions. So it increases exponentially. That's why it leads to computational complexity, high calculation cost. Like, like there are so many possible combinations. That's why it requires high calculation cost. Coalition instability. Suppose we take some political parties. If they get better rewards, then they will lead to those parties which have better rewards. Uncertain coalition values. It is very difficult to find the estimating the actual value of cooperation between the players is very difficult. Suppose let's take a business partnership, and they both are aligned in some business, and they are maybe, suppose they are expecting some profit, and suddenly a market situation changes. Then they can't expect they can't have some expected value as they are expecting. The same thing. Calculating Shapley value. Shapley value, the Shapley value for player I represents their average marginal contribution across all the possible ways. Order of journey, like A to B, B to C. And like Monte Carlo sampling is nothing but like suppose there are 10,000 students in a college, then if you want to find the score of then you don't have to take all those 10,000 students. You just take 100 randomly select 100 students and take the average, and we can heuristics. We can ignore the players which are giving negligible contribution. You can use this in AI coordination, smart grids, and economic systems.